have learned in the previous module that the potential of an individual half cell cannot be measured. You can only measure the difference between two half cell potentials, which gives the EMF of the cell. If the potential of a half cell is arbitrarily chosen as the standard, then the potential of the other half cell with respect to the arbitrary standard can be determined. Arbitrarily, the standard hydrogen electrode is chosen as the standard reference electrode. The standard hydrogen electrode consists of a platinum electrode coated with powdered platinum inside a glass tube. The platinum electrode is dipped into a 1 molar solution of hydrogen ions, and pure hydrogen gas is bubbled in at 1 bar of pressure. The standard hydrogen electrode is designed to carry out the half reaction shown here. A hydrogen ion plus 1 electron produces half a mole of hydrogen gas. By convention, the potential of the standard hydrogen electrode is assumed as 0 volts. When all ion concentrations are 1 molar, reduction potentials are called standard reduction potentials or standard electrode potentials. The standard electrode potential of an unknown half cell is determined experimentally by combining it with the standard hydrogen electrode. The EMF of the resulting galvanic cell is determined using a voltmeter. As the potential of the standard hydrogen electrode is assumed as 0 volts, the measured EMF itself becomes the standard electrode potential of the given half cell. For example, the standard electrode potential of a zinc electrode is determined by combining it with the standard hydrogen electrode and then measuring the EMF. The EMF of the cell is calculated as the potential of the right electrode minus the potential of the left electrode. Therefore, the EMF of the cell is equal to 0.76 volts. Thus, the standard electrode potential of zinc is equal to minus 0.76 volts. The negative value of the standard electrode potential indicates that zinc can reduce the H+ ions. Similarly, the standard electrode potential of copper is calculated as shown here. The positive value of standard electrode potential indicates that cupric ions get reduced more easily than H+ ions. In other words, hydrogen ions cannot oxidize copper. Thus, copper does not dissolve in HCl. On the other hand, copper dissolves in nitric acid due to the oxidation of copper by nitrate ions. The values of standard electrode potentials of some electrodes are shown in the table here. If the value of E0 is greater than 0, then the reduced form of the species is more stable than hydrogen gas. If the value of E0 is less than 0, then hydrogen gas is more stable than the reduced form of the species. As can be seen from the table, fluorine, with the highest standard electrode potential value of plus 2.87 volts, shows the highest tendency to get reduced to fluoride ions. Hence, we can say that fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent. Lithium ion, on the other hand, with the lowest electrode potential value of minus 3.05 volts shows the least tendency to get reduced to lithium metal. Thus, lithium ion is the weakest oxidizing agent, and lithium metal is the most powerful reducing agent in an aqueous solution. You can also see from the table that as the value of the standard potential increases, from the bottom to the top of the table, reactions show a greater tendency to undergo reduction. The strongest oxidizing agent are found at the top, while the strongest reducing agents are found at the bottom of the table. As the value of standard potential decreases, half reactions have a greater tendency to oxidize. The reactions in the table need to be flipped to write out the oxidation half reaction, and the sign for the electrode potential changes. That is, the standard oxidation potential is equal to minus standard reduction potential. Try to answer this question on your own before checking the answer. Which of these is the strongest oxidizing agent? The nitrate ion, elemental iodine, or the dichromate ion? Answer: the dichromate ion is the best oxidizing agent. As shown in the table, it has the most positive reduction potential. Sometimes, inert electrodes, such as platinum, gold, or graphite rods, are used in voltaic cells. Inert electrodes provide a surface for electron transfer to occur, but they don't participate in the reaction. If inert electrodes are used, then the electrodes do not change in size as the spontaneous reaction proceeds. The potential difference between the two electrodes gives the cell potential. For voltaic cells, the cell potential is always positive. To calculate the EMF of the cell, add the potential for the cathode half reaction and the potential for the anode half reaction. The electrode with the positive reduction potential acts as the cathode, while the electrode with a negative reduction potential acts as the anode with respect to the standard hydrogen electrode. We'll develop our skills by completing a practice problem. Consider this situation. A student constructs a voltaic cell by connecting a half cell containing silver wire immersed in 1 silver nitrate and a half cell made from aluminium wire immersed in 1 aluminium nitrate. Identify the anode and the cathode in the cell. Write the balanced net ionic equation that occurs. Calculate the EMF of the cell. Identify the direction of electron flow in the circuit. Identify the direction of ion movement through the salt bridge. Which electrode will get larger? Which electrode will get smaller? There's a lot to do here, so we'll work through the problem one piece at a time. Let's start by consulting our table of standard reduction potentials. The silver half reaction has a higher standard reduction potential than the aluminium half reaction. This means that silver has a greater tendency to undergo reduction than aluminium. Since silver has the higher standard potential, silver will undergo reduction. Aluminium has a greater tendency to oxidize So, we will need to write an oxidation half reaction for aluminium. Since reduction occurs at the cathode, silver will be the cathode in this voltaic cell. Aluminium must be the anode, since oxidation occurs at the anode. Now that we've identified the anode and the cathode, writing the half reactions is easy. At the cathode, a silver ion gains 1 electron to form silver metal. The value for the standard reduction is plus 0.80 volts. At the anode, aluminium metal loses 3 electrons to form an aluminium ion. Compared to the standard reduction potential table, we have flipped the reaction. Notice also that the sign of the electrode potential changes as well when we write the oxidation half reaction. We need to balance these half reactions to show the conservation of change as well as mass. To do this, we must make sure that the number of electrons lost equal the number of electrons gained. In this problem, we need to multiply the cathode half reaction by 3. However, reduction potentials are intensive properties. Note that the value of E0 for the reduction half reaction is unaffected. Now, we are ready to find the overall balanced equation and calculate the cell potential. Adding up the two half reactions gives the net equation. 3 moles silver ions react with a mole of aluminium metal to form a mole of aluminium ions and 3 moles of silver metal. To calculate the cell potential, just add the cathode and anode potentials. We get E cell is equal to plus 2.46 volt. We have enough information now to draw a diagram of our voltaic cell. Electrons will flow through the external wire from the aluminium strip, the anode, to the cathode, silver. When the switch is closed, anions will flow from the salt bridge into the anode compartment, and cations will flow into the cathode compartment. As the cell runs, the aluminium electrode will get smaller, and the aluminium ion concentration will increase in the anode compartment. The silver electrode will get larger, while the silver ion concentration in the cathode compartment will decrease. Consider a voltaic cell, such as the Daniell cell we studied earlier. If an external opposite potential that is less than the cell potential is applied, the reaction will continue in the forward direction. If instead an external opposite potential is applied that is equal to the cell potential, the reaction stops altogether. There will be no current flow. If the external opposite potential is larger than the cell potential, the cell will now run as an electrolytic cell. The reverse reaction will occur. Electrochemical cells have a variety of uses. For example, pH meters use electrochemical cells. Electrochemical cells can also be used to measure solubility product constants and other types of equilibrium constants. They are also useful in potentiometric titrations.